The IO-Link communication standard is changing the way we think about getting data from the sensors on our factory floor to the systems that we use to control, monitor, and visualize data. If you're interested, stay tuned. I'm Matt Nygaard, a business development manager in our industrial products group here at PCB Piezotronics. Today, we're going to show you how to create a simple visual solution using IO-Link enabled sensors, masters, and lights to monitor vibration in rotating assets on your factory floor. First, we're going to take inventory of the parts that we need in order to create the solution. Next, we're going to show you how to configure those parts. And then last, we'll quick do a demo using tools that we have here at PCB and show you how it all works. Okay, let's get into it. Let's talk about what we need to assemble to make this solution work. First is our PCB Piezotronics 674A91 vibration sensor. We have a SICK Industries SIG series master gateway solution, an IO-Link enabled stack light, a couple of M12 cables to connect light and sensor, and 24-volt power. That's it. Okay, I've taken a little time off camera to connect my system together. I've applied power, I've connected my sensor into port 1, my light into port 2. Last thing I've got to do is connect my IO-Link master to my laptop so I can start the configuration of the software. So we've got our computer open, we're connected directly to our master, and the first thing that I do is I type in the default IP address for my IO-Link master. That gives me direct access to the web server that's being put up on my IO-Link master from SICK, and quick access to my configuration tools. The first thing that you have to do when plugging in a sensor is upload an IODD file. That's my library of device data that this master needs to understand what the sensor, or here the stack light, is trying to tell it and how to represent that data. Those can be easily found on a public library at ioddfinder@iolink.com, and you can search easily by manufacturer or part number, download that file, and upload that to your master in a matter of minutes. Next, I want to do a quick check and make sure that my device is connected and reporting data, which it is. And then I want to look at an IODD view, which gives me access to look at my process data to make sure everything's being reported and I'm getting that cyclic data of peak values, of crest factor, of temperature, which you can see represented here. The device also promotes and pushes up some additional data, not consistently, but will report the vendor name, serial number, and other product data that are important for people using the device. All right, so let's head over to the logic editor portion of the configuration tools from SICK and start building our application. What you can see in the logic editor is that this tool gives us access to all of our process data. These are the values coming in not only from our vibration sensor, but also our IO-Link stack light. You can see here I've already started and built my application for peak velocity, but I've also pulled a couple of blocks in from the perimeter to show you I can have temperature ready to go to start building with next, or my peak acceleration. I've also got on the right side here process data values from my IO-Link stack light. And I've coded tier 1 to be green, I've coded tier 2 to be yellow, and I've coded tier 5 to be red. These are read-write. So what I'm going to apply here is some logic that says in a certain condition I'd like to trigger my green light, or my yellow light, or my red light. So we're going to start and show you how I've built this application for peak velocity. So we're worried today about some misalignment, some softness, a loose foot, and we're going to try and trigger for that by building first two different constant values. I'll call this my warning and my critical threshold. Those constants can be, value blocks can be easily pulled from the left here. I'm also going to use some compare blocks because I want to compare my incoming data against those static values. My constant for my warning I've programmed at 10. My constant for my critical threshold I've programmed at 50. So to find my compare block, I need to go into conditional. I'm using a float and a comparator, and I can simply drop and drag that compare block in when I need it. So let's start with our peak velocity and compare that for our good running condition. This is when we have data coming in under a certain threshold and we want to show with our tier 1 that we are green, that everything's okay. So what I do is I compare and draw a line from my peak velocity to my compare value and my constant to my compare value. So I'm comparing those two values, and I draw a line from my less than over to my tier 1, which is green. So anything that comes in that's less than 10 is going to show me green and tell all my operators that everything's okay with my machine. Now I want to show that there may be a warning state. So I build another compare block and I compare my constant value with my peak velocity again, but this time I'm saying anything greater than or equal to should trigger yellow. But first, let's keep in mind not anything greater than, I want it to be less than my warning. So what I do is I add an additional compare block of my incoming value against my critical threshold and say that also anything less than. So anything greater than my warning, anything less than my critical, combined with an AND statement, will turn my stack light yellow. And then final, we want to compare against velocity and my critical threshold and show that anything greater than my critical threshold will turn my light red. That's it. And I'm done with my logic that will run consistently, concurrently on this device. All I do is have to apply this logic to my IO-Link master and I'm ready to go. And remember, this works independently outside of a network. And again, to access these tools, I do it through an IP address. So it can easily sit out on a factory floor, triggering your stack light for the data coming in real time, but also could be configured remotely so that you don't have to get down on the factory floor to change some of these threshold values. So that's it. Let's take a look at how this is happening and working in real time. Now that we're done configuring, as you can see, I've unplugged my laptop from my IO-Link master. I've put my stack light on a pole, and I've connected my sensor to an asset. Today, our asset's going to be a portable vibration calibrator from our industrial products group here at PCB. The portable vibration calibrator simulates a vibration signal coming from an asset. So what we're going to do is we're going to increase the amplitude on our portable vibration calibrator, and what we'll see is the output increase from our peak velocity measurement that we set our thresholds for. So as we increase the amplitude, you'll see that we move from a green to a warning indicator, and if we really crank it up, stimulate something really going wrong with our asset in terms of our alignment, what we'll see is that we get into that critical threshold of a red indicator. Really important for people on the factory floor to see what's going wrong. And that's it for our solution today. If you want to learn anything more about IO-Link or any other products at PCB, please go to www.pcb.com. Thanks.